Good morning and welcome to AP Statistics. So this begins our 2 week of out-of-school distance learning, and hopefully it won't be a problem for anybody. The expectations are simple. Every morning, as you have already gotten used to, there will be a Google Classroom announcement that the video is posted and the assignment is posted, and you're well aware of what to do by this point. So here's what I'd like. It'd be great if you could watch that video earlier in the day so that when it's time for our class around 11:40 or so, you could join me for a Google Meet to ask questions about that material. Kind of like a flipped classroom, but I'm doing both parts of the flip. So you'll watch the video, learn some material, take some notes, maybe try the homework, and then if you have questions, you'll join me for the Google Meet at the regularly scheduled time so that you can go over whatever you are worried about and have problems with me. Make sense? I think it's the best way to move forward and get the most out of our time. That being said, today I'm going to be bouncing around between the school and home, trying to get materials I need to move forward for the rest of the 2 weeks. So today I won't be hosting the Google Meet. This video will be the grand sum total of today's instruction, and it's a lot of material anyway to cover, so please bear with me, take some notes, watch it more than once, pause it when you have to, and let's move forward from here, okay? We start chapter 2 today, which is location in a distribution. Now, the graph that's on the board is something you should already be familiar with. It's called a normal distribution, and there was an insert unit which you should have learned in a previous year, last year, I believe, that talks about what we're about to look at. But it's okay if you don't remember it or didn't quite understand it. I'm going to go over it now. This is called the normal distribution, a normal curve. It's called normal because it peaks in the center, it tapers off to both sides symmetrically and forms asymptotes with the horizontal axis. All that being said, you might have heard of it as a bell curve. We don't use that word because a bell curve really is just too generic. Any curve distribution, whether it's skew left, skew right rather, or normal, is a bell. It's kind of like calling a square a rectangle. It's not wrong, but it's not right either. So we're going to call this a normal distribution. I've denoted for you in the middle, mu, the population mean. The center of the distribution of a normal curve is right there in the center, as is the median and the mode, but we aren't as concerned about them right now. To the left and right of the mean are sigmas. Negative sigma, positive sigma, -2, +2, -3, +3. Sigma, again, being the symbol for standard deviation, which we've already gone over how to find. Standard deviation is the average distance of a data point to the center in a distribution. What you might notice here is that within -3 to +3 sigma from the mean, it's a lot of the distribution. There's almost all of it covered already. There's something called the empirical rule. And I'll write it out for you. Empirical. And the empirical rule, which again, I believe we talked about a little bit before breaking, was 3 special numbers. It's 68, 95, 99.7. The empirical rule tells us that in a standard normal distribution, within 1 deviation below to 1 deviation above the mean is 68% of our data. Now that's a lot of our data, but take a look at it. It's all this in here. The tallest part of the curve obviously contains the greatest area, and area is percent of data contained. So within 1 standard deviation below and above our mean is the vast majority of our distribution. Now, within -2 to +2 sigma from the center is 95% of the data. Now again, obviously that is showing us a great deal of data. So in 95% it's all this stuff, including the middle 68. So within 2 standard deviations above and below the mean is 95% of everything within the distribution. It's quite a lot. And of course, you can see that 99.7% must be what is -3 to +3 sigma, standard deviations above the mean, 99.7%. So that's so much that it's almost the entire distribution. So you got to ask yourself, what is outside 3 standard deviations away from the center? As you would imagine, we call those values outliers. I'm not sick. It's getting on towards 10 p.m. So we have 99.7% of our data contained within 3 deviations below to above the mean. That's almost everything. 0.3% of our data is contained outside that range, making them almost certainly statistical outliers. Okay? We obviously have the formula for outliers, but this is kind of a graphical representation of where an outlier would be, and the extremes in those little teeny bits in the tails. Okay. So part of chapter 2 is concerned with where values fall with relation to the other values in a distribution. So we're going to come up with a way to figure that out with a simple number, and that number is called a Z-score. I'm going to erase what's on the board, so make sure you've written it down, or just, pause and rewind. Why am I worried about you? Should be more worried about me right now. So let's erase that. And I'm going to put on the board a very simple equation. It's called your Z-score. The Z-score is just a number that tells you where you fall in relation to the pack. How far above or below the mean do you fall? As a measure of the mean, your data point, and the standard deviation of the distribution, the average distance to the center. Here's what it is. X, which stands for the data point, minus mu, which is, of course, the mean. You might remember x minus mu, or x minus x bar, from when we were calculating standard deviation. It's one of the first things we did. It's the deviation from the data point to the center, divided by the standard deviation of the distribution. Well, if I take the distance from center and I divide it by the standard deviation, I find out how many standard deviations away from the center my data falls. The further away from center it is, the more unusual the data point is. So as a for instance, if on a certain test the mean score was an 80 and the average distance to center was 3 points, and you, being super smart, got a 92. What's your Z-score? Again, it's a standardized measure that tells the viewer how far from center they were. So let's plug that in. Your Z-score is equal to your score of 92 minus the mean score of 80 divided by the standard deviation of 3. 92 minus 80 is 12. 12 divided by 3 is 4. Your Z-score is 4. Now, does that make you good, bad, or indifferent? Think back to the empirical rule. Within 3 deviations above or below the mean is 99.7% of the data. So where does a Z-score of 4 fall? Well above the outlier range. 3 and above would be an outlier. You're 4. You're 4 standard deviations away from the mean. You're exemplary. What if we took a different person's score and reevaluated that? Hopefully you understand what's going to happen right now, but let's put the number 80 up there. 80 was the mean score. So a person who scored 80 is how many deviations away from the center? Well, 80 minus 80 is 0, and 0 divided by 3 is still 0. That person's Z-score is a 0. Does that mean they did badly? No. Did they do well? I mean, it depends on the distribution. 0 is the mean. The person scored the average score. If it was a great test and everyone scored a 95 or above, then a Z-score of 0 would have had the person still getting an A or an A+, even though it's a Z-score of 0. It's relative to the rest of the distribution. It could be good, it could be bad, it could be indifferent. We don't know yet. All depends on context. Okay, so let's say a person did poorly. I mean, they didn't do terribly, but they did not as well as the rest of the group. They got a 74. Now, 74 minus 80 is negative 6. And negative 6 divided by 3 is negative 2. So this person's Z-score is negative 2. Again, what does it mean? Did they do well? Did they do badly? Did they do indifferently? Well, again, negative 2 means this person was 2 standard deviations below the average test score. Now, that's obviously not encouraging. But did they fail? No, they got a 74. It's not bad. Just relative to the rest of the distribution, they didn't do very well. It's always going to be contextual, relative to the distribution. Keep that in mind. So z-scores can be positive, negative, or 0. They can also be decimal values. I didn't do any just now. They're all integers. They don't have to be. You could be negative 1.12345 z-score. It's not a problem. There could be fractions of a standard deviation between you and the center. It's not an issue. I just chose integer examples just now. Well, let's use some algebra. I know that you miss it. Who wouldn't? My friend got a score of 84 on a test on which the average score was a 92. He's told that his z-score is negative 1.3. What was the standard deviation of this test? Algebra. The z-score formula has 4 variables, z, x, mu, sigma. So remembering that z equals x minus mu over sigma, we could just plug in what we know. Z is negative 1.3, x is 84, mu is 92, sigma is the unknown. Well, 84 minus 92, what is that going to be? Well, 84 minus 92 is going to be negative 8. Over sigma, how do I clear a fraction? I multiply by the denominator. In this case, well, it's sigma. So negative 1.3 sigma equals negative 8. Divide both sides by negative 1.3. The standard deviation is 8 divided by 1.3. Hey, I lost my calculator. Oh my gosh. Well, what would that be? I'll be right back. I'll just talk to you while I'm walking away, so that way it's more like I'm really in the room with you. While I get my calculator, which wasn't next to me when I started this process, which I guess, is a little bit of an oversight on my part. Oh well, guess what? I'm back. So I got my calculator. Oh, and dessert's ready. So we have, I'm going to say 8 divided by 1.3. Obviously negative over negative, still positive. So I get a 6.1538. 6.1538. Go to 4 decimals. The standard deviation of this test was 6.1538, so the average person scored within 6.1538 points of the center. We can find for any one of those 4 variables if we have 3 of them. Okay. Algebra portion of the day is done. The z-score portion of the day is covered. Talked about the empirical rule and showed you a normal curve. Okay, so one more thing I'm going to try to focus on today, and that's what's called linear transformations. Sounds like fun, doesn't it? I know, it's a long video. I apologize, but what else we got to do? So, we have, in any linear equation, like you're used to in Algebra 1, y equals mx plus b, we kind of, for reasons unknown, change it a little bit for statistics. So, we're going to say y equals a plus bx. Again, I don't know why, but we do. So y equals a plus bx rather than mx plus b. It means the same thing. A is still the y-intercept, b is still the slope, but it talks about how we can change data. Sometimes you even see this. We'll say that x sub nu, that's a weird w, equals a plus b x sub old. I'm changing the data, right? A plus bx. If I plug in a number for x, I'm doing some transformations to it. B in this case is the multiplier. So I'm going to multiply whatever it is by b, and then I'm going to add this A value, whatever it happens to be, it's a constant shift versus a multiple shift, which is B. I get a new number out of it. So that's really what every linear equation is. You're plugging in an input X, you get out an output Y. You've transformed your data based upon some predetermined equation. So let's take an example of how this is going to be affecting things, okay? Let's say that in a distribution, the mean salary is $50,000 of a company, and the standard deviation of said salary is, I don't know, let's just go with $10,000, make it easy. All right, so what that means is within 3 standard deviations, within $30,000 of the center, 50, we had 99.7% of our distribution, provided it's a normal distribution. Okay, great. Well, what happens most years, maybe not this year because of our fun financial situation, but most years you get a raise, all right? Some years you get a bonus, which is a kind of a flat increase, a constant value. And you also get, let's say, a percent increase. You'll get a 5% raise. So you're going to be making 105% of this year's salary next year, and maybe even with a bonus. These are the 2 numbers I'm talking about, the A and the B, okay? So let's say on a given year, we're just getting a bonus. It's a flat increase. Now, if I have Y equals A plus BX, and I'm giving a flat increase, which value is that, the A or the B or the Y or the X? Well, hopefully you understand that a flat increase is the A value. Everyone's going to get $5,000 more, but I'm not giving you a multiplier. I'm not going to give you a kind of a shift, no percent increase. So everyone's salary is going to increase by $5,000 plus their last year's salary. Well, there's my transformation of the linear data, which was salary. What's going to change? Well, let's see. Basically, what it means is if we had a normal curve that was centered at $50,000, and I give everyone a $5,000 raise, what's the new curve look like? Well, it's going to shift forward by $5,000. And now it's centered at $55,000. So a constant shift, the A shift, will change the mean. Let's make a little chart here of what's changing, okay? So with A versus with B. So I didn't do a B shift just now. Just focus on A, the constant increase. What changed? Well, the mean definitely changed because I added $5,000. What about the median? Will the median change also? Well, I already said in a normal curve, the mean, median, and mode are at the same point. So yeah, the median is also $5,000 more. Okay, what about other important measures of center, like, I don't know, the quartiles, quartile 1 and quartile 3, well, they have changed. Well, again, yeah, the whole thing is shifting forward. So Q1 and Q3 will have changed. How about the IQR, the interquartile range, the distance between Q1 and Q3? They all shifted up, but did the distance between them change just now? Well, no, that stayed the same. Just they both shifted up, but the distance between them remained the same. What about the standard deviation, the average distance from center to any data point? The whole distribution just shifted forward $5,000. Did the distances between points change? No. What about the range of data from the lowest to the highest? Did it change? No. It all shifted forward $5,000, so its location changed, but distances did not. There's really no distance. There's no difference, rather, in measures of spread right now. Okay. Well, what about with a B shift, a phase shift, if you will? What if everyone gets, in addition to the $5,000, they also get a 10% raise? My phone keeps shifting with battery issues. 10% raise. That means that in addition to the $5,000, you're getting a 1.1 multiplier. Why is it 1.1? Well, a 10% raise is the 0.1 part, but they didn't lose the rest of their money. So it's 1.1 last year's salary. That's what a raise looks like. Now, Will the mean change with a multiplier like that? Well, of course, they're getting a 10% increase. The whole thing is shifting. The mean changes. Will the median change? Yes. Just like the constant, the quartile 1 and 3 also will. But think about what that shift will do. It's spreading out now. The richest people get even richer compared to the poorest people. A person making $1 million a year getting a 10% raise, that's an extra $100,000. But a person who got 20 grand a year with a 10% raise only gets $2,000. It's a $100,000 versus $2,000 raise. They both got 10%, but their differences are expanding. So what else is changing? The distance between points. So that means that in addition to the same measures of center that A affected, we're also going to find a difference in the IQR. It's spreading. And we're also going to find a difference in the standard deviation. It's shifting. We're also going to find a difference in the overall range, because now that's growing also. And it did not change with just the constant shift. Measures of center and spread will both change with a linear transformation. Okay, there's obviously more to do. But what I want to do is just tell you what your homework assignment is and let you wrestle with that. And then on the Google Meet tomorrow, we'll rehash this, go over the homework, and you can call in and ask me any questions. What I want you to do is on page 101, just numbers 13 through 16. So, and that's going to be on the classroom announcement anyway, but page 101, numbers 13 through 16. We probably have covered enough for you to understand what you're doing, but if not, again, wrestle through it and then write down any problems you have, and then we'll work them out tomorrow. One more quick thing. On a standard normal distribution, the center, as we determined already, was 0, and the standard deviation was units of 1. That was the standard normal curve. Center at 0, positive 1, 2, 3 sigma, negative 1, 2, 3 sigma. I think that question might come up in the homework. So that's what a standard normal distribution looks like. The center is always a z-score of 0 with increments of 1 for standard deviation. That's all for today. So please, hopefully it was clear and workable, and you can go through the homework and do well, but write down any questions you have, and we'll go over it tomorrow and have a Google Meet. Have a great day.